So let's look at another example of chi-squared here. So this involves gene expression. So suppose that we have 4 different genes. We're going to label them A, B, C, and D. And they're expressed in the following proportions: 9/16 for A, 3/16 for B, 3/16 for C, and 1/16 for D. So those are just the probabilities or proportions expressed as fractions. They total up to 1. And we want to use a chi-squared test to determine if the observed data here indicate that the gene expression differs significantly from theoretical values. So we had a sample size of 160. 86 in the sample expressed gene A, 32 gene B, 28 gene C, and 14 gene D. And then the theoretical frequencies, we would take our 160 and multiply it by 9/16. So that's n times p sub I. And then as a decimal, so that's actually, let's see here, 160 times 9/16, 90. And then 160 times 3/16, 30, 160 times 3/16, 30, and then times 1/16, 10. So our null hypothesis then is going to be that the proportion expressing gene A is equal to 9/16. You could write that as a fraction or decimal. The proportion expressing gene B is 3/16. Gene C also 3/16. And then gene D 1/16. And then the alternative hypothesis is that at least one of those probabilities is different. So at least one p sub I differs from the null hypothesis. Our test requirement is that all of the expected counts here have to be greater than 5. That is true. And now we will figure our critical value here. So our degrees of freedom, we've got 4 groups. So 4 minus 1 is 3. And then we want 0.05 level, so chi-squared 0.05. So if we go to our distribution calculator, we've got 0.05 for our area, 3 for our degrees of freedom. We want the right tail 7.815. So we need our test statistic, chi-squared, to be greater than 7.815 in order to reject the null hypothesis. So here's our chi-squared distribution. And we've got 7.815 out here. And rejection region is to the right. So then our chi-squared test statistic, we've got observed here and expected here. So observed frequencies, that actually should be O sub I, and this is E sub I. So you can do this chi-squared test statistic nicely in a spreadsheet. You tell it to subtract these 2 columns. So you can do O sub I minus E sub I. So 86 minus 90, negative 4. 32 minus 32, 28 minus 30, negative 2, and 14 minus 10, 4. And then you can do O sub I minus E sub I squared. So just square these values. So negative 4 squared is 16. 2 squared 4. Negative 2 squared is 4, and 4 squared 16. And then you'll take those values and divide them by the expected. So we get relative amounts. So this 16 will be divided by 90. the 4 divided by 30, 4 by 30 again, and then 16 by 10. And then convert those to decimals if you want. And then the sum of those is our test statistic. And that value turns out to be 2.04, approximately, as a decimal. And we see that 2.04 would be over here somewhere. It's not in the rejection region. So this chi-squared here is less than 7.815. So we do not reject H0. So formally, we would state that there is not sufficient evidence to conclude that the alternative hypothesis is true. So our alternative, remember, is that the probabilities differ from H0. So that is, the probabilities differ from the theoretical value. So there's not sufficient evidence to conclude the probabilities, the p sub i's, differ from theoretical. So based on this data, we can conclude that these observed frequencies are behaving in the same way that we would expect them to. Now you can compute your test statistic and then also the p-values. You can use a p-value method for this on the TI-84. You enter your observed values in the first list and your expected values in the second list. So let's do that real quick. So we will go to Stat and then Edit. And you want to clear out your lists if you have them. We'll just overtype since we've got 4. So I want my 86, 32, 28, and 14 in the first list. And then that second list, we want 90, 30, 30, and 10. So we entered those as a list. Then we go to Stat, Tests, and then we want the chi-squared GOF, goodness of fit. So that is option D. Observed in list 1, expected in list 2. Our degrees of freedom, it tells us, are 5, but our degrees are 3, so we need to change that. So 3 groups here. And then we can either calculate or draw. If we go ahead and draw here, it'll sketch the chi-squared distribution curve. So, and let's see, there we go. So there's our chi-squared distribution curve. And this blue, that is the area past the test statistic, which is the p-value, which is 0.5632. That's greater than 0.05. So there's our chi-squared 2.0444. That agrees with what we got here. And then our p-value is 0.5632. So we note here that our p-value is equal to 0.5632. That is greater than 0.05, which was our alpha. So again, we do not reject H0. So it drew this area past the 2.04. So it's not sketching the rejection region, it's sketching the p-value when you ask it to draw. If you do calculate, it'll just give you these values without the drawing. So you've definitely got a way to double check here. So I may have you do one problem by hand, but for the most part, we'll be using technology to do these. And then just to get an idea of what output looks like for this chi-square goodness of fit in software, Jamovi Here's some sample output here. So this is looking at state data by the psychological profile: friendly and conventional, relaxed, creative, temperamental, uninhibited. So here we had 48 states that were surveyed here, and then these are the proportions. So those are observed proportions. And then the chi-squared test statistic right here was 6.5. Our degrees of freedom were 2 because there's only 3 groups, and our p-value was 0.039. So this is saying that these values, these counts here, differ from the expected values because our p here is less than 0.05. So at the 0.05 level, this would not follow the expected distribution.